All right, so in this video, we're going to be looking at the definition of a linear transformation and going through the steps to prove that a matrix or some other type of expression satisfies the definition of a linear transformation. Now, sometimes you'll find that the notation for linear transformations takes a little bit of getting used to, but basically the notation here indicates that our transformation T applies to the vector x and then maps that vector x onto the operation A times x, where A is a matrix that satisfies the dimensionality needed to perform that operation. And so this notation indicates that A is a linear transformation, or T is a linear transformation from x in Rn to AX in Rm. Again, the matrix A can transform the vector to a different dimension depending on its size. If the following conditions hold for every vector u and v in Rn and a real scalar c. So these are the requirements. If I apply the transformation to the sum of u and v, then again, this is basically function notation. If I apply the transformation to the sum of u and v, then if I apply the transformation to u and the transformation to v separately, I have to get the same answer if I add them up. If I have a scalar and I apply that scalar to u and then I apply the transformation, I have to get the same answer as if I applied the transformation to u and then multiplied by the scalar. And I have to have that the transformation applied to 0 produces the 0 vector. Now, these properties are very similar to properties for testing for whether a system, whether a space is a vector space or a subspace of a vector space. So it can be useful sometimes to think of these in concert with each other. All right, now, because they are, in fact, related concepts. So what we're going to do is we're going to look at this in the context of a matrix, and then we're going to check to see that it satisfies all of the conditions. Now, as was noted, the third condition technically is entailed by the other two conditions, particularly the first condition. But sometimes that's going to be the easiest one to check if the definition is going to fail. And so I usually include it in the list just because it is so useful for disproving if a matrix is a linear transformation or some other operation. All right, so let's look at our A transformation, and we want to check this again with generic vectors, because we have to establish this as a proof. So we can't use specific vectors. We have to use vectors that contain any real number. So u will be u1, u2, and v will be v1, v2. And since our matrix is a 2 by 2 matrix, these vectors are the right size that we need to multiply by the matrix A. Now we're going to test our first condition, which is that if I add my two vectors together first, and then apply my transformation, I get what answer do I get, and then I'm going to compare that to the result of applying the transformation to each vector and then adding them up. So in this case, if I apply my transformation to the sum of my components, essentially this matrix is going to switch the order. It's going to put the two subscripted components in the top and the u1 subscripted components in the bottom. And so if I split these up into the u components and the v components, I get u2 u1 plus v2 v1. And if I apply them separately, so this is going to flip the order, u2 u1, and then this one will also essentially flip the order, v2 v1, and we can see that the results are the same, and therefore it satisfies this condition. Now we also do the second one the same way. we multiply one of our vectors by the scalar, and then we apply it to the transformation, and we see that it does flip the order again. And then we apply it to the vector, and then we put the scalar on the outside last. And here the transformation flips the order, and then we multiply by the scalar, and we get the same answer again. So this satisfies our condition. And if we let the two components be equal to 0, we do in fact get 0 as required for that last check. Therefore, we can say that because it satisfies the properties of our linear transformation, it is in fact a linear transformation. Now, we can also apply this definition on functions. And in this case, we're going to assume that b is not equal to 0. So this is ax plus an actual non-zero constant b, and not just ax. Now, the easiest one to prove here that this is in fact not a linear transformation under the definition we've provided is it true that f of 0 is equal to 0? And in fact, it's not. F of 0 is equal to b. Now, this may seem a little bit confusing at first, that this is obviously a linear equation. It is a straight line after all, but it does not actually satisfy our definition of a linear transformation. Technically, when b is not 0, we would actually consider this an affine transformation in linear algebra, which is to say that it's linear plus a constant. In some context, you will sometimes see this actually referred to as affine. In the context of linear algebra, this is not linear. It is affine, and it has other properties that can be satisfied, but in this context, it does not satisfy this definition of linear algebra that we mean when we talk about linear algebra. So even though it is a linear equation in the algebraic sense, it is not linear in the sense of linear algebra. Now, if b was in fact 0, then this would satisfy the definition of a linear transformation. So y is equal to ax would be fine, but not y equals ax plus b. And again, sometimes that can seem a little confusing, but we're just defining linear a little bit differently here than we did in pre-calculus or in beginning algebra. All right, so here we want to find out if the derivative operator is a linear transformation. So again, think about our definitions. So the derivative operator operates on functions, so we'll call our generic functions f of x and g of x. And so what we need to know in order to test this are our properties we already know about derivatives. So you don't have to go back to like the definition of the derivative or anything else. We already know what these properties are because we proved them in calculus. So if I take the derivative of a sum of two functions, it is the case that I can distribute the operator and I can take the derivative of one function and then add it to the derivative of the other function. This is already a property that we know, and so this satisfies our first condition. And same thing for our second condition. If I have a function multiplied by a scalar, it is okay to take the scalar out and then take the derivative of the function and then apply the scalar. And that is a property that we know from calculus. And this satisfies our first two conditions that are required. We can also double check that third extra condition that in fact, yes, the derivative of 0 is in fact 0. So it does satisfy the conditions of a linear operator, but here on a function space and not on a sort of traditional set of vectors. Now, if we want to do this for the integration operator, we can also go through those same properties to see if we get a linear transformation or not. So I'm going to use this definition of the accumulation function. And if I as my basis function, my transformation. And so we're going to look at our properties of antiderivatives. And it is true, again, that when you are taking the antiderivative of term by term, you can split them up term by term. Same thing when you have a scalar multiple, you can pull them out. And part of the reason that I defined this transformation so carefully is in order to satisfy that third condition, because when I'm integrating from 0 to 0, then I will also get that third condition satisfied, which is that if I plug in the 0 function, I will get 0. And then finally, we want to look at an example that's going to fail our checks. And in this case, we're going to look at this definition of a transformation. It's going to be applied to the vector x1, x2, x3, and it is defined as follows: x1 plus 2x2, the absolute value of x1 minus x3, and 1. Now, this is going to actually fail for a couple of different reasons. So we're going to kind of walk through why those individual things are going to create a problem. So the easiest one to check, as I said, when you have a function that's actually going to fail, the test of being linear, is to check this extra one that I added, that the transformation applied to 0 has to equal 0. And that's because in this last row, if I let this vector be all zeros, I'm still going to end up with the vector 0, 0, 1 because of this 1 here. So anytime you see an example transformation where one of the values has an extra constant, so like our ax plus b equation, that extra constant is going to make this linear definition fail. Now, if we were to consider the transformation without that 1 in it, would this be okay? Well, the 0 vector is okay. Now we would put in 0, 0, 0, and we would get 0, 0, 0 back out of it. But that doesn't make it linear. And so again, for showing that the definition fails, we can use specific vectors to show that it fails, because it only has to fail in one spot in order to not be true everywhere. And that's why when we're proving it that it is true, we have to use general real numbers, x1, x2, x3, and not specific values, because the fact that it works in one case doesn't mean that it works everywhere. If we use generic values, then we can show that it's going to work no matter what numbers we choose for those x1, x2, x3. But when we're trying to show that it fails, we just need to show that it fails in one place. So in this case, I'm going to check the addition property, the sum property, and I'm going to choose two vectors whose sums add to 0 in this case. So the vector u will be -1, -1, -1, and the v will be 1, 1, 1. So if I apply my transformations, I'm going to add these two up, and I'm going to get 0, and then we know from looking at the definition and testing the 0 condition, this does give me 0. But if I apply them separately, according to this definition, this is going to be -1 plus 2 times -1, which is going to be -3. And then this one, if I put in the absolute value of -1, that's going to be 1 minus a -3, minus a -1 is going to give me a 2. And then the last component, of course, is 0. And then if I apply this to the v vector, then this is going to give me 1 plus 2 times 1, which is going to be 3. And then this middle component, it's going to be the absolute value of 1 minus 1, which is going to be 0. Again, bottom component is 0. And if I add these up, my top component is 0, my bottom component is 0. That's great. My middle component is not 0, and that's because this absolute value. Now, it seems obvious to us that the absolute value is not linear. anytime you put in a reciprocal or an x squared function or anything like that, you should expect that the expression will not be linear. That's why that constant is kind of deceptive, because the constant seems like from our algebra days like that would be fine, but it turns out that it's actually not fine when we apply our definition for our linear transformation. And obviously, anything that is actually not linear is going to fail here as well, because the absolute value is not linear. Great. So we did not get the zero vector, and therefore we have established it fails at least one of the conditions, and therefore it is not linear. We can also show that it's not going to work on the second property as well, because if I take the transformation on V, I know that I got 3, 0, 0. But if I take the transformation and apply it to negative V, I get negative 3, 2, 0. And so, in fact, if I apply that negative 1 on the outside of my transformation for V, I get negative 3, 0, 0. And these are not equal to each other, and therefore it also fails on that second condition. So you don't, when you're proving that it's not linear, you just need to find it to fail in one spot. You don't need to prove that every condition fails, because sometimes one of the conditions will be fine and one of the conditions won't. You do also have to be a little bit careful sometimes to not use vectors that contain lots of zeros and ones, because sometimes it will work on 0 and 1 and it won't work on other ones. So for instance, if we were squaring something, doing the transformation on 1 would do something different than if you're doing the transformation on a component that was 2. So sometimes it does take a careful choice for your components in order to actually verify that the definition fails, because it might just work on the example that you used, which is why when you're proving that it's true, you need to use the generic components. And when you're proving that it's false, you can use specific components.